Inference about two population proportions. Simply put, we are using this to see if two proportions are part of the same population. We assume they are as the null hypothesis, but if we are disproved, we go to the alternate, obviously. We pull the data to make a pooled point estimate, and a pooled point estimate should just be the pooled proportion. I'll explain it in the next one, or actually, I don't know if the formula is here. But first, you have to distinguish between dependent and independent sampling. And simply, independent sampling is when one does not affect the sampling outcome of the other. And dependent is if one does have an effect. And typically, they do have an effect if you sample without replacement. But if the population is big enough, you should be fine. So, and that's why we always assume that the thing is 5% of the total population. So testing hypotheses about two proportions from independent samples. So the null hypothesis, and let me just erase this, is always going to be that the proportion and the sample proportion, because we can't obviously measure the full proportion, is equal to each other, or P1 equals P2. So that means they share the same distribution. And by doing so, they share the same point estimate. And a point estimate is just going to be x1 over n1 plus n2 plus x2 is the formula right here. And simply put, we use that because we assume that the proportion is we assume that the pooled proportion is going to be used as the center point right here, and we assume that it's actually the population proportion. And basically, we calculate the test statistic, again using z-scores. The formula is slightly more complicated. So the pool proportion formula is simply the proportion of the two separate groups. So we have 10 over 60 with headaches, and 30 out of 80 in headaches. It is 10 plus 30 divided by 80 plus 60. Formula again. Here's the actual formula. So we use P1 minus P2 to ensure that there actually is a difference. You could also use P2 minus P1. And then the P right here is just pooled proportion. And if you distribute this, you actually get, I believe, the standard deviation of the sums of the standard deviations, or the sums of the variance, I believe. And then you square root that. And variance is just the standard deviation squared. Simplified, we're just taking the sums of the variance and square rooting them. We simplified that into the formula for some reason. I'm not sure why they didn't just distribute, but I guess it is easier that way. So these are the conditions again, that the sample times the proportion must be greater than 5. So the expected values must be greater than 5. And of course it must be less than 5%, so we don't sample without replacement. If the z-score is higher than the alpha, then we could say that the alternate hypothesis is too far outside the range of standard error to be counted for remote qualitative analysis. And basically, if it's too far outside, then we can assume that they're two different sample means deviating from the same population, or the same pooled proportion. So here's constructing and interpreting confidence interval. Same thing, just P1 minus P2, except P1 minus P2 is the difference, plus or minus the z-score, times this. Now, I'm not really sure how this works, actually. And I'm not going to try to figure out right now. I mean, I'll probably look it up later. But I'm not sure how this works, but I do know that the I don't know why they don't use the pooled proportion again, and they just use the individual proportions. But it's just the z-score times the square root of the added variances, except this time it's not. And you're also dividing by n1, which is a little bit strange. I'm not really sure how it works, but this is the confidence interval. So we use this to calculate when using the classical method or the z-score approach for null and alternative hypotheses. Determine the sample size necessary. Here, there are two formulas. One with prior point estimates, which is the rearranged formula. So it's n equals z-score minus error. So I'll just write z, or over error squared. So over error, and I'll just write e, I guess. Times the point estimate one, which will be 0.1, 1 minus point estimate, and I think it's divided by n, or no, it's plus second point estimate, plus p2, 1 minus p2. There we go. And I'm not sure how it works again, but here's the formula for it. So 1 without prior estimates, which assumes that the point estimates are equal, it is the n equals 2 z-score error. And that's just using some simple algebraic manipulation. So it's z over e. Forgot the formula or the symbol for standard error, so I'm just going to be using e. And then 0.5 squared. So simple algebra. That's how you calculate confidence intervals and calculate the sample size necessary. So